Hello, this is Tim Malloy with video 2-4 Equilibrium. So let's get started with problem number 17. One end of a uniform 4.4 meter long rod of weight Fg is supported by a cable at an angle of theta equals 37 degrees with the rod. The other end rests against the wall where it is held by friction as shown in the figure below. The coefficient of static friction between the wall and the rod is μs equals 0.515. Determine the minimum distance x from point A at which the additional object, also with the same weight Fg, can be hung without causing the rod to slip at point A. So we are solving for this x in this photo. And so what I did is I took this photo and I made a torque diagram out of it. So first things first, we'll put Fg at the center of mass. And I believe they said the rod was uniform. They did. Okay, so we can assume that. And then let's do this tension force by the rope. It's at an angle, so it has a vertical and horizontal component. And then I'll move on to static friction. So obviously there's static friction keeping the rod up, I suppose, and making sure it does not slip. So that's all covered. And we also have this, oh wait, I'm sorry, I didn't write it in. We have this Fn by the wall. And then I'll get into these two horizontal forces in a second because it's very important. And then at some distance x from point A, we have another Fg, placed somewhere we don't quite know. Remember, closer to the hinge/point of rotation means smaller torque. That's why the question is asking minimum distance x. Okay, and now write our givens. Length of the rod, theta equals 37 degrees, μs equals 0.515. And then our force equations we are going to do now. Torque, let's do that later. But force equations, remember the system is at equilibrium. That is the name of this web assign after all. So we only have two horizontal forces. Makes it pretty easy for us to just set them equal to each other, and that'll be the x equation. And then the vertical equation is pretty similar. Forces pointing up would be Ft's vertical component and static friction. And then the forces pointing down would be our two Fg's. And we can just both call them Fg. It's not torque. We don't have to factor in distance. We will get to distance later, but not quite. So actually, let's do that. Let's do that torque equation right now. We'll be rotating about this point A. So first off, with the forces that would cause a counterclockwise rotation. Wait, no, I'm sorry. A clockwise rotation. We have Fg at some point x from point A. And then we have Fg at the center of mass 2.2 meters away from point A. And then objects causing a counterclockwise rotation, or a positive one. Ft, it's Ft's vertical component, again, because these horizontal ones are balanced and they cancel each other out. So Ft, and then we have the perpendicular distance, which is something I struggled with initially. But just remember that you basically just form a triangle with this Ft, and then you shoot out what am I trying to say? Oh, you shoot out a perpendicular line to the Ft, and then you grab that distance there. Pretty easy. And then we will come back to the torque equation later. But you'll notice that in these equations we've got there's just a whole lot of forces to deal with. So what I decided to do is kind of combine these x and y equations. So where am I? Okay, I took y, and then I subbed in Fn and coefficient of static friction for the static force. And then what I did is I I substituted this ft for fn. That was pretty easy. And I believe I simplified these out, and I got about this 2ft, which carries down here. And then I set that equals ft. I divided, so we have ft equals 0.507 ft. And then something that I was very proud of figuring out on my own is that we're actually going to be dividing these equations. So here, let me make this a little prettier, so that way you can understand it better. I just put the FG down there, like, okay, of course we'll divide, so these cancel, and then these cancel as well. Bring it down, x plus 2.2 meters equals 5.22 meters. Subtract, final answer. The distance, the minimum distance of that FG ball from point A is about 3.02 meters. So some final takeaways. Dividing equations is tough. It's something most people don't think to do, including me. Remember perpendicular distance. It's what I initially was doing was I was just like considering, the vertical force is the only one affecting this rod's rotation. So let's just do the distance from point A to the vertical force. But you cannot do that, even though the vertical force might be the only thing causing rotation. That horizontal component still, I guess, influences the distance you take. And then it's essential to always set up your two force equations and a torque equation to solve the problems. And you can kind of understand how you can weave your path through the equations and solve for whatever you need to solve for. Okay, that's it for the video. Thank you.